In this video, we will see how we can use Caret to use different models to classify our outcome, and then to choose between these competing models as the best model. And then we'll make this determination based on a resampling method called cross-validation. And then we'll also see, once we have found our best specifications among competing models, how we can use these best specifications to then classify our test data set, and then to choose the best model among those for our test data set. And then finally, once we have decided on what model to then pick, the steps that are needed to then use our best model to classify or score new data. So let's load the relevant libraries. And then the data set that we will work with is universal bank. Our outcome variable is personal loan, so whether the customer took out a loan from our bank or not. And then we will just label them to be the first level as the yes or the target level. And then we will remove the unnecessary variables. We'll also create a factor variable from the various education categories that we have. Once we have pre-processed or cleaned the data, we can do the split. Now again, we will create an 80-20 split where 20% will be our holdout of the test set, and we'll build the model on the training set, which is the 80% of our data set. And the resampling method that we will follow is a 5-fold cross-validation, and we will repeat it 3 times. And then we will also obtain these are the 2 arguments needed when we are dealing with classification outcomes. We will say summary function is toClass summary, and then we'll also let the model give us the class probability. So class probability is equals true. And then we'll allow for parallel processing. So this sets up the type of resampling or the control function that will again be called by the train function in Caret. The 3 models that we will run are ElasticNet, where we will tune over the alpha, which is the mixing parameter, and lambda, which is the extent of penalty that the model will be imposed. Then we will run random forest, and then we'll just tune over the number of variables to be chosen for each decision node. And we'll create a grid from 1 through 4. And then we will also use the stochastic gradient boosting method, where we will tune over some of the settings allowed by Caret. So we are running these 3 models. So our job is to, based on 5-fold cross-validation repeated 3 times, pick the best tuning parameters for ElasticNet, then pick the best tuning parameters for random forest, and then pick the best tuning parameters for the GBM method. And then we will look at the best of each of these 3 models, and then we will see how each of these best performing models from these algorithms does on an average on our validation set, and then we will use that to find the predictions on our test set and see how good a job the best of each of these 3 models does on our test set. So we'll set up the grid. Search, we have set up the training function. For ElasticNet, our grid will be the values of alpha and lambda. And just to keep things simple, we will tune over a sequence of lambdas ranging from 0.01 to 0.1. So we are giving it less penalty, and we'll tune length 3. Then for alpha, we will tune over a sequence of 0.0 to 1 with a 0.1 increment. For random forest, we will just let the number of variables chosen at each split be ranging from 1 through 4. And we'll also, instead of choosing which of these parameters to tune for GBM, we will let Caret determine which ones to tune. And the Caret's tuning will be based on interaction depth and number of trees. It will leave the other 2 at the default value. So this is the train function that we are specifying. For elastic net, we are choosing our elastic net grid, and then we just have to say the method glmnet. We will choose the best model based on ROC, and that is why we needed to specify two-class summary and class props equals true. Without this two-class summary, we would not have been able to get ROC, and the model would have trained on accuracy. For random forest, we can just change the method to RF. So this is how easy it is in Caret to run different algorithms. And then we will change the method to GBM. Now, one thing that we have to be mindful of is that each of the models that Caret runs has their own set of tuning parameters. So we have to make sure that the tuning parameters being called in the tune grid match up with the tuning parameters that Caret allows. So for random forest, the only tuning parameter that we have is number of variables to be chosen, called mtry. So our tuning grid had just that. For elastic net, we tune over two parameters, which are alpha and lambda. So our grid should have column names alpha and lambda that we will use to train this. So we run the grid, and we can just look at our GBM elastic net grid, and we have the various values of alpha and lambda that we'll be tuning over. Similarly, when we look at the grid for random forest, we will get these values. So it'll tune over mtry equals 1, 2, 3, and 4. And then we will let the model choose, think tune length equals 5. So what we're telling Caret is to choose each of the tuning parameters to have 5 possible values and create a grid from there. So again, by default, in GBM, Caret tunes over entries and iterations. So it's going to create 5 values for entries and 5 values for the interaction depth, or the depth of the tree. And then create a grid interacting those 5 values and then tune over them. We can click on this button, and then it's going to take a while to tune. And after the tuning happens, we can look at the models that come out for elastic net. Once the algorithm has run, we can obtain the results of elastic net. These are the parameters over which our tuning happened, and the model determined that the best value of alpha is 0.25 and the best value of lambda is 0.01. So there's very slight penalty being given to the number of x's, and alpha being smaller to 0, closer to 0 than to 1 means it is more of a ridge regression that gets chosen. And as we can see in our tuning grid, for alpha equals 0.25 and lambda equals 0.01, which corresponds to 0.25 and 0.01, our ROC is 0.96. Again, this is the average ROC of doing our k-fold cross-validation repeated n times on the validation set that Caret creates. For our random forest, the model chose number of x's to include at each split, ranging from 1 through 4, and the best accuracy was when the number of variables to be chosen was 4. So this is the tune parameter of GBM for random forest, and then we can see with GBM, again, Caret created 5 values for interaction depth, so the number of splits to have on a tree, and also the number of trees to build in each round, ranging from 50 to 250, and then 1 through 5 for the tree depth. And it also held the other values at the default setting. So this is a fairly efficient way, instead of trying to fine-tune the grid. If we were to decide to go with GBM, we could then tinker with more of these combinations. We could try a number of trees to range from 0 to 100 with increments of 100, and then see which one does well. Interaction depth, by increasing it too much, we may be overfitting, so we may not tinker a lot with this specific parameter. Then once we have these, so here we get ROCs separate. We have to find out the ROCs. We can also compare how each of these models performs in a very elegant way. So there's a function in Caret called resamples, which requires a list. Let's say that we ran 5 models. We could create a list. We give each model the name and then the actual object that we are using. So here when we have 3 models, elastic net, random forest, and stochastic gradient boosting, we can create a list of these. And then once we look at the summary, we get a very nice summary stat of what the models were, and then the performance on each of these models' best tuned parameters on the cross-validation set. So on an average, elastic net's ROC was 0.96, whereas random forest ROC was 0.9979. And there's a pretty close tie between random forest and stochastic gradient boosting. They both have very comparable ROCs. Then we also get results on sensitivity and specificity. Sensitivity is the model's ability to correctly identify class 1 among all class 1. And sensitivity and specificity is the ability to correctly identify all class 0 among all the class 0s. So here we see that the random forest does well on our 5-fold cross-validation repeated 3 times. But how do these models perform on the test set? That's what we will look at next. So our test set, remember, we had not used that so far. We'll just use our holdout or test set to assess the quality of fit of the best elastic net model that we got, of the best random forest model that we got, and of the best GBM model that we obtained. So we can now predict the outcome or the probability on the test data from elastic net. And once we run that, we get the probabilities associated with outcome 1 and that with outcome 0. But it doesn't give us the class. We can obtain the class by picking out the column name of the majority class and assigning that as the label. So that's what this code chunk does. And then we re-level it to have yes as the first level and no as the second level. We can do the same for all the others. And then here we are, because later on we will plot lift curve and ROC, so we'll just have the model names as a separate column. So I'm just creating another column called Enet, and I'm binding it with my results for Enet. So if you look at the head of this, we get Enet. So elastic net will be indexed by Enet, RF for random forest, and then GBM for GBM. So we will then stack each of the model's outcomes to a data set, which we can then use with group by to plot the AUCs and the lift curves. So we can do the same process for each of the 3 models. We will get the predictions on the test set. Then we will bind the name with the predictions and also classify anything above 0.5 as a success and then re-level that. So doing this, we will get 3 data sets each, which has the model predictions for one of the 3 models. So this is our Enet, then we get our random forest, and then this is our data set of model probabilities and predicted outcomes for GBM. And then we can stack it, and this index model will help us group them when we create some of the metrics we'll need to assess the models. To get the confusion matrix, the syntax is data refers to our predicted class and references the actual class. So in confusion matrix, we need the class value, not the probability, to get the confusion matrix. So the first argument or data is the predicted class from our model, and references the truth in the data. So our reference is the actual personal loan class for the test set. So this gives us the usual confusion matrix statistics. It gives us the accuracy, sensitivity, specificity, and then our positive classes, yes, because we had relabeled the data for the first class being yes and the second class being no. So for each of the three data sets, we'll just now combine and bring in our actual class as the fifth column. So running this combines our data sets. So if we look at our GBM hat, for example, we will see that it has now bound the lone class or the actual class with our predicted class. So the next set for interest might be to draw the lift curve. So for lift curve, we will use the lift curve function, and then we will use ggplots autoplot to automatically plot it. So let's work with just one class. So we have our model dataset random forest hat. We'll pipe this model, and lift curve needs two arguments, the actual class and the probability of the class. What is the model probability? So our actual class is the actual predicted class, and yes is our probability that our model assigned to that individual belonging to class 1. So notice that this is the prediction and this is the truth. So once we generate the data for lift curve, we can pass that to plot, and this is our lift curve. So for our random forest, our lift for the first decile is almost 9. So our model is doing almost 9 times better than nature in identifying class 1, at least for the top decile. And this is how we can read the lift at any of the percentiles in the data. Now let's see we can get the lift curve for all 3 models. So we'll just bind our data set, or we can just do a header of my model. So this is basically a stacking of all our outcomes. So the first stack will be Enet, the next stack will be random forest, and the third stack will be GBM. So we have our class 1 probability each model gave us, the predicted class, and then we have bounded with the actual class. And then we can pass on this. We'll use the group by function to then group our results by each model and then get the lift curves. So once we run this, we get the lift curve for each of these models. We can do the same for AUC or the ROC curve. We will use the group by function. And once we run this, we get the ROC for each of these. We see that random forest has a slightly higher ROC. GBM is pretty close, but they definitely do better than the elastic net. And we can summarize the results with an ROC table. So in our model's assessment on the test set, random forest's AUC is 0.998, which is in fact slightly higher than the AUC it got on the cross-validation set. So our model has done pretty well. GBM is pretty close as well, 0.996, and they are better than the elastic net. So now what happens? We have done a horse race among various models. Between the various models, we have done hyperparameter tuning. If we wanted to deploy one of these, we could now start tweaking one of these models more. But let's say we are set. We have chosen the tuned parameters for random forest. So we want to see what those parameters are. We can use best tune function. This gives us that the best tuned parameter value was with mtry was 4. Now, as the final step, before I can use my model to score new data, I have to rerun the model with the best tuned parameters on the entire set, and then use that result to score new data. Otherwise, we lose information because we have already split our full set into training and testing. So now once we have finalized our model and the tuned parameters, we should rerun the model on the entire data set. To run that, we don't want to do any resampling, so we can say the trainControl method is none. So this will not do bootstrapping by default or any of the cross-validation sampling procedures that we can choose. We are just saying don't do any cross resampling. We'll still get the class probability, will allow parallel processing. So this has set up our control function, and then to specify the tune grid, we will just say use the specific value of the grid. Now the grid has to be in a data frame, but the default outcome of this is the data frame. So we will just pass our mtry equals 4 into the tune grid. So once we run this, the object we get from best RF, we can use this object to predict our outcome on the new data. Now suppose we wanted to work with GBM. We can do the same thing. We'll look at our GBM best tuned values, and they were entry equals 150. The depth of the tree is 5, shrinkage 0.1, and this is again, these are the default values that Caret did not work with, but now we'll have to create a grid with these specific values and then pipe them into the train function and then run GBM on the training the entire data set using these values. So all we need to do is, again, set up the fit control, as we said, no tuning, and then no resampling. And here we can pass our GBM grid into our tune grid function. And then what we obtain with best GBM can be used to predict new data.